So, welcome back. We have been looking at this algorithm AO star, which is used to solve an AND OR graph. And as we discussed in the last session, the algorithm maintains a graph G and it works in two phases. In the forward phase, it traverses the graph and it traverses that using markers that it has maintained, saying that this is the best choice at any given point of time. It goes to a set of unsolved nodes u that we said, and it picks one node n from u and refines that node. So, it has picked n and it has refined it and evaluated their heuristic values as the case may be. So, this is a forward phase. In the backward phase, which is here, I am just drawing an arrow upwards to reflect the fact that it is backward. The algorithm of course goes from top to down. In the backward phase, it backs up the values from the children of n. So, first it will decide what are the costs associated with the children. So, let us say if this cost is 10 and this cost is 12 and this cost is 9 and this cost is 14, and if the h cost is, let us say for the sake of argument, is all 2. So, then this is 10 plus 12 22 and 4 26 and this is 9 plus 14 23 plus 4 is 27. So, it says that this is the best choice. It starts by doing that. So, let us say the value of n was 24 h of n as given to us by some heuristic function. So, this 24 has now gone to 26 and therefore, it needs to propagate this up to all the ancestors, and that is what the backward phase does. Now, let us talk about admissibility of this algorithm, of the algorithm AO star. Like the algorithm A star, algorithm AO star is also admissible, that is, it finds the least cost solution when heuristic function underestimates the actual cost. Now, if you think about this algorithm, you will see that it is following the broad schema that we have been talking about all along, which is to refine the best looking partial solution till the best solution is fully refined. And the best solution is refined would be reflected by the fact that the root node would be labeled as solved essentially. But now, what we are saying is that this algorithm would be admissible when the heuristic function underestimates the actual cost essentially. And the argument for that, which we will not go into detail, is, or the explanation is same as before, that as long as the partial solutions which are yet to be explored are looking better, it will keep exploring them better than the fully refined solution, even if we have found one essentially. So, it will not terminate with the first solution it finds, because some other solution may look like it might be cheaper. So, it will explore that before actually terminating. We saw that in the case of Brunson bound and also in the case of A star. We will do this by taking a problem, another small example, and modifying the problem in two ways by changing the h cost associated with transformation. So, in one case we will keep the h cost very low, which would mean that it is the heuristic function is actually overestimating the effort that is required. In another case, we will keep h cost as high, which would mean that the heuristic function would be underestimating the actual effort required, and we will see how the algorithm performs differently in both the cases. Like we did in the case of, for example, A star, when we looked at W A star and so on, we saw that the more emphasis you give to the heuristic function, the faster it converges, but it may not converge with an actual solution, the optimal solution, and that is the point we want to illustrate with AO star as well. So, here is a problem that we are trying to solve. The values in the nodes are the heuristic values as given by some heuristic function, and we have not mentioned the h cost here because we are going to look at two h costs, but in the first case we will assume the h cost to be 1. So, let us look at a sample here. So, if you are looking at this branch where it is the heuristic values are 4 and 5, if you add 1 and 1 here, then it becomes 4 plus 1 5 plus 5 plus 1 6, and so this would become 11. You can see that the actual value of 21 is overestimates. But you can also realize that because of the fact that it is overestimating the cost, when it looks at a more refined version and the more refined version appears to be cheaper, it would kind of be committed towards that, and it would rapidly go towards whichever solution it finds first in some sense, and that is exactly like what best first search algorithm would have done without actually taking into account the actual cost. So, here in this example we will assume that the every R cost is 1. All the nodes, internal nodes are labeled with heuristic values, and solved nodes are represented by double line squares, and we will assume for the sake of argument that the cost of solving the primitive nodes is 0. So, the only cost is associated with the edge cost, which is how much transformation you do before you reach a set of solved nodes essentially. So, let us work first with h cost equal to 1, and remember that we are starting with this root node which has a value 21, and this is how the algorithm begins. We will show the node that is to be expanded next. This is node n, which is selected from the set of unexpanded nodes u in a bold square, and proceed to expand that. In the first case, of course, there is only the start node. So, you expand the start node, you generate the 4 children as we saw in the previous example. The better option is on the right hand side, and it results in a cost of 11, which is 4 plus 5 plus 1 plus 1, remember. The other side would have been 7 plus 6 13 plus 2 15. So, 15 is of course not selected, 11 is selected, and that is how what is reflected in the partial solution or the graph that we have expanded so far. So, we also have the marker which says that this is the better of the two edges. So, algorithm will in the next cycle go down this marker, and it will have to choose between one of the two nodes 4 and 5. Let us say for the argument, let us say it chooses node 5, and if it does that, then it would have expanded the node that follows. Now, you can see that node 5, what was originally the value 5, has now been reduced to 2, and that is because it has got 2 children and they are both solved, and we said that solved nodes have cost 0. So, the only cost 2 that we have is the cost of these two edges 1 and 1, and the value has gone down from 5 to 2, and correspondingly the value of root has gone down from 11 to 8 essentially. It was 11 in the previous case and it is 8 now. So, you can see that the effect of overestimating is to, as you refine one particular solution more and more, it becomes cheaper and cheaper, and you get more and more committed towards that essentially. So, you can see that there one can think about why it does not find the optimal solution. I will leave this as a small exercise for you to find out what is the optimal cost for this problem that we have given, optimal solution, and does the algorithm find it. So, here of course, there is only one more node left, which is the node which has value 4. We refine that, and in this particular example, this value 4 has now gone to 8. It has actually gone up, and that is because in this particular node the heuristic function is not underestimating, is not overestimating, it actually underestimated the cost, and therefore, we will see that it will end up doing a bit more work essentially. So, this node can be solved in two ways. One is with two children 3 and 4, the other is with one child 7. So, 7 plus 1 is 8 and that is what is reflected here. So, this is the best choice as marked here. This would have been 3 plus 4, 7 plus 2, 9, but 9 would not be selected. So, 7 is the best choice to be marked here. We had said that this node value 4 was underestimating. We find that the revised value of 8 also was an underestimate. It refined this node which had a value of 7 and that has gone to 9. So, I should draw an arrow like this. So, this as we will see in the next slide, it has gone to 9 and therefore, its attention would shift to the other side essentially, or rather it has gone to 10. That is because its child was 9. So, 9 plus 1 10 and 10 plus 1 this side is 11 and that side was 3 plus 4 7 plus 2 9. So, 11 has been rejected and 9 has been selected and attention shifts to the other side essentially. Let us say we select this node which has a value 3 to be this thing and we find that it leads to a solve node in one step. Its value has gone down from 3 to 1 and therefore, this its parent has gone down from 9 to 7 and its own parent has gone down from 13 to 11 essentially. And so, the marked path is shown here. Observe that the markers are maintained in other parts of the graph as well, but we will never reach this part of the graph unless this marker were to somehow shift this thing. We will see that can happen if we underestimate the cost. At the moment, we are overestimating the cost. So, this phenomena is not likely to be seen. So, once it has gone down this path, it will stick to this path. It refines this node 4 next and we find a solution now. It has also been reduced to a cost of 1. So, you can see that the total cost is now become 8 and this 8 has come because there are 8 edges in the solution 1, 2, 3, 4, 5, 6, 7, 8. The only cost is cost of transforming and this is the solution it has found. So, you can see that except for the fact that this 4 that we see here was actually an underestimate, it had kind of committed to whatever it is exploring first and terminated rather fast. Let us now take the same problem and assume that the edge cost is 10, which means that the original values are likely to be underestimates essentially. So, we start as before with the root node which has an estimated cost of 21, but now we assume that the edge costs are 10. So, of course, the first node will be defined in the same way, the same subgraph would be generated, but now the edge costs are 10. So, we have 10 here, 10 here, 10 here, 10 here. So, this is 4 plus 5 9 and 20 which is 29 this side and this is 7 and 6 13 and 20 which is 33 this side. So, 33 is obviously rejected and 39 is selected. So, like before in this case, because it is a symmetric situation, each hyper arc had 2 edges. So, each of them contributed to 20 each to the transformation problem and 4 plus 5 was cheaper than 6 plus 7. So, it also marks the same this thing. But notice that from 21 the root has gone up to 29 and that is a property that we saw in A star also, is that as you refine the solution further or as you move closer to the goal, the estimates which is the f values in that case monotonically increase. So, here also if the heuristic function is underestimating, you will find that the estimated cost will increase essentially and that is a property of an underestimating function. So, as before, let us say it selects this node which had a value of 5 and again it found 2 nodes which were the solved nodes, but now earlier this instead of this 20 it was 2, but now it is 20 because it is 10 plus 10. for the two edges. So, its cost has gone up, and suddenly we find that this side has 20 plus 4, 24 plus 20 is 44, and that is rejected, and the marker has shifted to this side. So, this is a phenomena that we will see more often when the heuristic function is underestimating, because as you refine a solution, it becomes more expensive, or it starts looking more expensive, and some alternate solutions may start looking better. And by doing that, the algorithm is going to explore more of the search space and not leave out the optimal solution at any stage, and which is what would end up in it finding the optimal solution, because it does more exploration than when you are overestimating. So, you refine this node with a value 7, and you find that even that has gone up, but in this example it has only one choice. So, there are two nodes left, 3 and 4. So, let us say it picks the node 4 and refines that. So, that was the node that it refined last, but because its value has gone up, and from 4 to 10, the overall solution from that time has gone up, and the pendulum is again shifted towards this side essentially. So, it refines this thing, which is also was labeled as 4, but that has now two choices. Now, when we looked at this solution last time, the left choice was better, but now the right choice seems better, because this one, because it has only one edge, and remember the edge costs are the ones which are contributing more. So, it goes ahead and refines that, and this remains the preferred choice, as opposed to this. When we solved the problem last time, the solution from this side was composed from here, and the other solution came from here, and that was the solution. But now, the preferred path is along this single edge, and you can see that because this is 9, this is 19, and this is 29, which is cheaper than going on the other side essentially. So, and so on, it explores more and more. It has made 29, but now the pendulum has shifted, as you can see here. So, it is now going in this direction, and it has refined this, and it has solved one side of this and edge here, and now it shifts its attention to the other side, which has the heuristic estimate of 6 here. So, when it refines that 6, it turns out that that 6 has gone up to 10, but still that is, and again the pendulum is shifted to this side here essentially. So, you must keep track. I have not worked out the exact values that are changing, but you must do this on pen and paper yourself and see that indeed the pendulum is shifted. This value 69 that we see is actually coming from here, and we have not written the other side what the value was. We can imagine that this is 0 plus 10. So, this is 10, so, and this is 40. So, that is 50 plus 2 would be 70 this side, and that would be rejected. So, 69 is coming from this side. So, you go and refine this node 9, and we will see that this node 9 now has gone up to 10, and it has gone to a value 70, and at this point the root gets labeled as 70, and it has found the solution, which is a different set of nodes. So, to solve the root node here, we have this AND arc, these two form still part of the solution, but the other side is formed by one single node here. So, there are 3 nodes in the final solution, and which is different from the solution which was found earlier. When it was overestimating, these 2 nodes were part of the solution, or rather this node was part of the solution, but it is a different solution. What is important here is to realize that the number of expansions that AO* did when it was underestimating was more. So, in some sense it is made sure that it is not missing out on the optimal solution before finally terminating with a solved root node. So, this gives us a general picture of the algorithm AO*. It is quite a neat and simple algorithm. But you might recall that we had looked at mean sense analysis, which was the work of Newell and Simon as part of their general purpose strategy. And you can think of what was happening there as also similar to what is happening in the AO star, in the sense that it is goal based reasoning essentially. So, you are comparing the current state to the desired state, and you are looking at the differences between them, and then you are trying to reduce the largest differences. So, you can see it has a backward flavor to this whole thing, and you are looking at this operator differences table and to solve it, and the means and the operators are the means and the differences are the ends, and that is why its strategy was called means ends analysis, that you analyze this and form a solution. And if you might recall that we had also looked at this diagram, which says that if you want to achieve a goal G from a state S, then you reduce the largest difference, which is a sub goal that you are solving. So, you solve that sub goal 1, and then you move to sub goal 2. So, let us call this sub goal 1 and 2, and it has the same flavor of problem decomposition, that you address one part of the problem, solve it, and then come back to the remaining parts of the problem. In this case, you can see that there were these OR choices here, and you selected this, and this also was broken up into its own sub problem, sub goal. So, let us call it sub goal 3, and then move on and so forth. So, the mean sense analysis also had a goal directed backward approach to problem solving, and that is quite similar to what we saw in the AND OR star algorithm. In the next few classes, we will look at approaches to problem solving, where again you decompose the problem into sub problems and solve them in a piecewise fashion. And in doing so, we will do two things. We will look at how rule based systems try to solve parts of problems, eventually working out the whole. We will also look at theorem proving in logic and reasoning, and see that one of the approaches in logic was also this goal directed backward search kind of an algorithm, but we will do that in the next few classes. Okay. So, we will see you then.